Why does a lone seesaw rider plummet to the ground? The answer to that question is that the lone rider produces a torque on the seesaw and causes it to undergo angular acceleration. The seesaw rotates such that the rider descends toward the ground and hits it. There are several ways of examining this situation, so I'm going to follow the path that I think is most straightforward. The rider's weight gives rise to a torque on the seesaw, and since the seesaw is no longer rotationally inertial, its angular velocity is no longer constant. Instead, that angular velocity changes with time, and the rider soon plummets to the ground. But those observations give rise to two more questions. How does the seesaw respond to torques, and what is the origin of this particular torque? So let me start by looking at the seesaw's response to torques. When the seesaw is experiencing no outside torques, it's covered by Newton's first law of rotational motion, so it rotates at constant angular velocity, like this. But once there is a torque acting on the seesaw is no longer covered by Newton's first law of rotational motion, and its angular velocity is no longer constant. Instead, its angular velocity begins to change with time. The seesaw undergoes angular acceleration. Angular acceleration is another vector physical quantity of rotational motion, and it is the rate at which angular velocity is changing with time. Like ordinary acceleration, translational acceleration, it's a subtle quantity. It's hard to see. You have to look carefully. It takes 3 glances to see acceleration, and it takes 3 glances to see angular acceleration. So I'm going to illustrate angular acceleration with my body and hope that you can see it happening. So here we go. Let me start motionless, rotationally motionless. That is, my angular velocity is 0. If I change my angular velocity during the time over which that angular velocity is changing, I am undergoing angular acceleration. So here we go. I'm going to undergo angular acceleration, and then I'm going to stop undergoing angular acceleration and watch what happens. Here goes the angular acceleration. It's going to be up. Right-hand rule again. I'm going to rotate. Here we go. Okay, I did it. It's over. I am now coasting rotationally at constant angular velocity. But when I first got started, I was undergoing angular acceleration. If I don't undergo angular acceleration again, I'm going to keep spinning here forever. And this will make me very dizzy. So I'm going to undergo angular acceleration downward in a moment. Ready? Get set. Whoop, there I did it. So during those 2 moments when I changed, extended moments, when I changed my angular velocity, I did it by way of angular acceleration. I'll show it to you again. I'm going to do angular acceleration upward for about 1/4 second. And then I'm going to do angular acceleration downward for about 1/4 second and come to stop. Ready? There. Now I'm coasting, and now. So the angular acceleration portion of that situation was during the changes in my angular velocity. Coming back to the seesaw then, the angular acceleration is absent now. Ready? Get set. There it is. There were a lot of angular accelerations there at the bottom, but they initially kicked in. The first angular accelerations kicked in when the rider got on the seesaw. Right now. So we see a torque causes the seesaw to undergo angular acceleration. But what if there's more than one torque acting on that seesaw at the same time? In that case, those torques add together to become a net torque, and the net torque is what causes the angular acceleration. So for example, if I've got 2 riders hopping onto the seesaw at once, the seesaw can't respond with several separate angular accelerations at the same time. It only has one. Instead, it responds to the net torque produced by those 2 riders. Well, if net torque causes angular acceleration, the question comes up is how much angular acceleration? It turns out that the seesaw's angular acceleration is proportional to the net torque acting on it. So if a gentle net torque acts on the seesaw, it undergoes a small angular acceleration. But if a large net torque acts on the seesaw, it undergoes a large angular acceleration. But there's a second factor involved in determining the seesaw's angular acceleration: the seesaw's rotational mass. Rotational mass is the measure of an object's rotational inertia, its resistance to undergoing angular acceleration. Now, traditionally, that physical quantity is called moment of inertia, and it has various complexities to it that are beyond the scope of our little discussion here, not relevant really to seesaws. So rather than trying to have you remember a name like moment of inertia with its complexities, I'll make our lives simpler by simply calling it rotational mass. That conveys the characteristic that it's a mass-like thing. It's a resistance to acceleration of some form. In this case, rotational acceleration. So, this seesaw has a certain rotational mass, a certain resistance to angular acceleration. So if I exert a certain torque on it, it responds with a specific angular acceleration. And I go back to putting a rider, so my little rubber stopper riders here. If I put a certain rider on this seesaw and let it undergo angular acceleration, well, it undergoes rather rapid angular acceleration, and down goes the rider. But I can increase the rotational mass of this seesaw by adding a second board. When I do this, I'm increasing the rotational inertia of the seesaw. Try to glue it and tape it in place. And now it's less responsive to the same torques as before. In this case, if I put one rider on, it undergoes angular acceleration, but not as much. Overall, the seesaw's angular acceleration is proportional to the net torque acting on the seesaw, and also inversely proportional to the seesaw's rotational mass. Those two observations form the basis for Newton's second law of rotational motion, which states that an object's angular acceleration is equal to the net torque acting on that object divided by that object's rotational mass. I'm going to ask a question about angular acceleration, but I'm going to do it in the context of a bicycle wheel that I can hold in my hands. At present, the bicycle wheel is motionless, and I'm going to do three things to it in sequence. First, I'm going to start it spinning. Second, I'm going to turn the wheel all the way around like this, so it's spinning the opposite direction. And now, as a third thing, I'm going to stop it from spinning. The question is, during which of those three steps was the bicycle wheel undergoing non-zero angular acceleration? All three steps involved angular acceleration of the wheel. When I started it spinning, it went from having an angular velocity of 0 to having an angular velocity toward you. Remember the right-hand rule here. When I pivoted it around like this, I reversed the direction of the wheel's angular velocity from toward you to toward me. That's angular acceleration. I had to make the wheel undergo angular acceleration to reverse its direction of rotation. And finally, when I stop the wheel from spinning, I take its angular velocity from toward me to 0. So all three steps required the wheel to undergo angular acceleration. So we see that a seesaw responds to a net torque by undergoing angular acceleration. Why then does a lone rider sitting at the end of the seesaw board exert a torque on that board? After all, the rider has a weight, which is a force, and if I hold the seesaw in place now, the rider and seesaw are pushing on each other with forces. The seesaw to support the rider's weight, and the rider pushing back on the seesaw in response. It's all forces out here. Where does the torque come from? Well, it turns out that forces and torques are related and that a force can produce a torque and a torque can produce a force. To see how that all works, let's go experiment with a door, because doors are a wonderful example of rotational motion and the use of a force to produce a torque. So here I am outside the physics building, opening and closing doors in a light rain. The things we do for science. Doors are a nice example of rotational motion. After all, they don't go anywhere. They simply rotate open and closed about their hinges. They have all the characteristics we've come to expect of rotating objects. They have angular positions, they have angular velocities, and they even have angular accelerations. But that brings us to the issue at hand, which is when you open a door, you do it by exerting a force on the door handle, and yet the door undergoes angular acceleration. Well, angular accelerations are produced by torques, not by forces. So how is it that a force exerted on the door handle produces a torque on the door? To show you how that works, I first have to define a center of rotation. Now, the obvious place to put the center of rotation is somewhere along the hinge line, because that's the line about which all the door's rotation occurs. But I have to be more specific than that, because center of rotation is actually a point, not a line. So I'm going to put the center of rotation in line horizontally with the door handle for reasons that we'll come to eventually. And that's going to be our center of rotation right there on the hinge line, aligned nicely with the door handle. Having done that then, let's look at ways in which not to produce a torque about that center of rotation starting with a force. So these are all the unsuccessful ways to try to open a door, some of which you may have encountered by accident. So, first unsuccessful way to produce a torque, starting with a force, is to push the door handle toward the center of rotation. So I'm pushing right at that center of rotation. No effect. I'm producing no torque. How about reversing my force? Instead of pushing toward the center of rotation, let me pull away from the center of rotation. Also, no luck. Doesn't do anything. So we see that pushing toward or away from the center of rotation is unsuccessful. How about pushing on the center of rotation? Let me come over here to the center of rotation and push right on it. I'll try to pull on it. All the kinds of forces. None of it works. So you can't produce a torque by exerting your force toward, away from, or on the center of rotation. Okay, now it's time to be successful. You can only take so much frustration. So now I'm going to exert a force out here on the door handle, not toward or away from the center of rotation, but at right angles to a special line. It's actually a vector. It's called the lever arm, and this is what the lever arm is. The lever arm is going to be the vector that extends from the center of rotation to the point at which I'm going to exert my force, namely on the door handle. So there is a vector that points along this line to this point here. It has a length of about 1 meter, about like that, and its direction is exactly to your left. And I'm going to exert my force not along that vector or with it or against it, but at right angles to it, perpendicular to that lever arm. I'm going to exert my force toward you, and watch what happens. The door undergoes angular acceleration and begins to rotate open. That is how to produce a torque starting with a force. If you exert your force at a lever arm from the center of rotation, that is the vector that extends from the center of rotation to where you exert your force, and you exert your force at perpendicular to that lever arm, then you produce a torque. And the torque has a specific direction. Its direction follows yet another right-hand rule. If you take your right hand and extend your index finger in the direction of the lever arm, toward your left right now, and then you sweep the index finger of your right hand in the direction of the force, which is toward you. So that's the sweep. Look what my thumb is doing. My thumb is pointing up. That is the direction of the torque I produced in pulling toward you on the door handle. The lever arm is that direction. The force is toward you. The torque I exert is up. And so it causes upward angular acceleration in the door, which swings open. Now, the amount of that torque that I produce depends on two things. One is how much force I exert. The torque is proportional to the force I exert. A gentle force produces a gentle torque. A big force produces a big torque. So, that's the first observation. Second observation is the length of the lever arm matters. The torque I produce is proportional to the length of that lever arm. Here I have a lever arm about that long. But if I go inside and I push near the hinges, I can make the lever arm very short. And watch what happens. Oh, that was hard. So I'm exerting my force here very close to the pivot, therefore at a very short lever arm, and I'm obtaining only a very small torque until I really crank up my force. We can combine these observations to relate the force to the torque it produces quantitatively. That torque is equal to the lever arm times the force, where only the component of force that is perpendicular to the lever arm is included, and where the torque is in the direction determined by the right-hand rule. So in this case, if the lever arm is pointing to your left and the force is pointing toward you, the torque is up. Now, this door is complicated because it has a closing mechanism. Like many doors, it has a system to try to keep that door closed when you leave it alone. So it's not free to exhibit rotational inertia. It has all kinds of its own trouble. And I had to overcome that resistance, that mechanism trying to keep the door closed. That's a lot easier to overcome if I'm out here with a big lever arm. I can exert a relatively gentle force on the door handle and get the door to open despite the closing mechanism. If I try to push very close to the hinges, that closing mechanism is hard to beat. And you may have had this experience that if you go to a door that isn't very well labeled and you have to push it open, you can't tell which side of the door has the hinges. If you push near the hinge side of the door doesn't open very easily. It's very resistant to opening because you're producing so little torque with your force. You need to go out to the other side of the door where you have a big lever arm to work with and therefore can really create a lot of torque with a small force. To produce a torque with a force then, all we need is a lever arm. For an unconstrained seesaw like this, one that can rotate in any possible direction, the options are limitless. I'm going to choose as our center of rotation the seesaw's center of mass, just for convenience here, right about there. And now let me show you a couple of torques. Things you've seen before, maybe some you haven't. If I come out here to a lever arm toward your left, and then I push down with my force, which is at right angles to that lever arm, or in fact, I don't have to be perfectly right angles. I just have to have some component that's at right angles to the lever arm. And I push down, I cause an angular acceleration toward you. Right-hand rule again. On the other hand, if I come out to a lever arm, same lever arm, but I push with my force toward you, watch what happens. I cause angular acceleration up. And if I come out to a lever arm toward you, very short one, but it's there, and push down, I cause angular acceleration to your right. I flip the board like that. Well, this is exciting, but very complicated. There are too many options with our unconstrained seesaw. So fortunately, we're going to focus on a constrained seesaw, one that has a pivot shot through the center that forces it to rotate in a very simple manner. This seesaw board down here cannot do this kind of rotation or this kind of rotation. And so it operates in a more simple fashion like this. And it still exhibits the same sorts of behaviors. To produce a torque on this seesaw, I come out to a lever arm and push at right angles, or partly at right angles to that lever arm, down, and I cause angular acceleration toward you, because my torque was toward you. We've seen how to produce torques with forces in the context of doors, in the context of seesaws, but what about another important household use of torques? Putting in or taking out screws or bolts. You rotate a bolt into a place and you rotate it the other direction to take it out of place. Well, suppose you have a big bolt like this that has rusted in place and you're trying to get it out, but it won't turn when you grab it with your hand and try to twist. You need more torque. So, in that case, you get a wrench. This is a device, and you will have to figure out how it works. This is a device that when you put it on the head of the bolt, it allows you to produce more torque. And by now you should be thinking about how this works. But what if this is really, really stuck and you need a bigger wrench? Well, that's already a pretty big wrench, you think. And you're probably thinking that I'm going to go over and get this wrench to show you the bigger wrench. But no, I have in mind this wrench. And so we take this wrench, put it on our stuck bolt, and lo and behold, it's a lot easier to produce a large torque on that bolt and remove it from wherever it's stuck. The question then is this: why is using this larger wrench more effective? Why does it enable you to remove that bolt when this wrench didn't do the job? This wrench has a longer handle, and it provides a longer lever arm with which to produce a torque using a force. So when you come out here to the end of the handle and push perpendicular to that handle, and therefore perpendicular to the lever arm, your force produces a larger torque as compared to this wrench. There's just not as much length here to work with. It's got a shorter lever arm, and so when you push on the handle of this wrench with that shorter lever arm, your force produces less torque. So we see whenever a lone rider goes out to a lever arm on the seesaw and sits down, the rider's weight gives rise to a torque on the seesaw that causes it to undergo angular acceleration such that the rider ends up pretty much sitting on the ground. The rider's weight is a force, and that weight causes the rider to push on the seesaw with a force, but the force acting at a lever arm from the center of rotation produces the torque that causes all this to happen. Pretty much the only place a single lone rider can sit or stand and not produce a torque on the seesaw is exactly on top of the pivot, which is kind of an interesting place to stand, and I must admit to having done that myself from time to time. But it's much more fun to have two riders on a seesaw, and that is the subject for the next video.